Yay!
Okay, hi Austin, hi Jolene. So here's the thing, at the top of your lab sheet for lab 6.1 modified limiting reactants, it says you have 25 milliliters of vinegar, but that's not true. We're going to use 40.0 milliliters of vinegar. So cross out 25 milliliters and write in 40.0 milliliters. So our goal here is to find out what the smallest amount of baking soda we can use to completely react with the vinegar. So neither is in excess and neither is limiting, but they both have exactly the right amount to complete the reaction. So our constant thing is going to be that 40.0 milliliters of vinegar. And then we're going to vary the amounts of baking soda to see if what we come up with mathematically actually happens in real life the way we expect. So, number one on the lab sheet, and by the way, the lab sheet is not part of your formal lab report. You have to write all of your calculations into the data and calculation section, not just turn in this sheet. You have to include a balanced equation and all that stuff in the lab report.
Do you still want us to turn in the lab sheets? Okay.
No, it's just to help you keep track of everything so that your data is all in one place when you go to write the lab report. So, number one says write a balanced equation for a reaction between vinegar, which is acetic acid or hydrogen acetate, and baking soda, which is sodium hydrogen carbonate. And since you guys haven't learned polyatomic ions yet, I will give you all that. The balanced equation for this is really easy because every coefficient is 1, which makes it a lovely thing to work with and takes out a lot of confusing parts. All right. Oh, really, that's not true. This is aqueous. What am I thinking? And this is in your book also after lab 6.1. Aqueous, that little thing there. So sodium acetate, that last compound, NaC2H3O2, is the stuff that they use to make vinegar-flavored junk food taste like vinegar. It's not actually vinegar, of course, because that would get it soggy. Sodium acetate. All right, so this is your balanced equation. It's just every coefficient is 1, so that makes it easy. All right, so then the component of vinegar that is the acid is this. This is acetic acid, and we need to find the molar mass of it. So everyone take a minute to do that. Find the molar mass of the vinegar. So take your periodic table, add up everything in the vinegar to get the molar mass. Oh, and just keep your lab sheet and your calculator and put all your stuff away while you're doing that so that we don't spill vinegar and stuff all over your things. Only 5. I'll have to do one.
2 carbons. 2 hydrogens. Oh, okay. That's 16. That's more. Oh.
Did you forget this 100 right here?
So
Yeah, I had 3 hydrogens at multiple.
and then 12.
There's 4 hydrogens.
Oh, there's 4 hydrogens?
Because there's the one in the front that breaks off when
Oh, wait,
it's
no,
an acid.
I wrote 3. I wrote 2. It looked like
Did you write that?
so that's
Yeah, 1%.
which therefore makes it 60.4. So.
Okay. So for you guys, we've got the balanced equation here. Acetic acid plus sodium hydrogen carbonate, which is baking soda, gives you water, carbon dioxide, and sodium acetate. All balanced. Every coefficient is 1.
Why did he give 1H and...
Well, in the book, I think he even writes the acetic acid as C2H4O2, But since it's an acid, you'll learn, like, in a later module, that the part of the acid that actually reacts is this hydrogen, and these three hydrogens are part of a polyatomic ion that sticks together. So chemistry-wise, this hydrogen is different than these three hydrogens. So this one's gonna break off and be the one of the two that forms the water there. And these three are gonna stick together as an acetate ion here. So we'll get there. So much to learn. So what do we have for the molar mass of acetic acid?
60.0 AMU.
Okay, so one molecule, since that guy's ionic, one molecule of acetic acid has a mass of 60.0 AMU. But for the molar mass, we always want grams per mole. So you're going to write it as 60.0 grams of acetic acid per 1 mole of acetic acid. And you really want to be careful to keep your chemical names in there so that you, number one, get practice writing them, and number two, use them to cancel. So it just makes it less confusing as you're building experience. Now we're going to find the molar mass of the baking soda, this sodium hydrogen carbonate.
Next one.
So if you have it, go ahead. Okay, Lily.
84.0 grams of NaHCO3.
Okay, so the molar mass of baking soda is 84.0 grams per mole. And now I want everybody in this room to just at the top of the paper or in a margin someplace record the temperature of this room right now, because we're going to need this in like module 12. And if we all write it down, then we'll have it. So the temperature of this room right now is right at 70 degrees, 70.0 degrees Fahrenheit. Let's take a Celsius too. Looks like about 21 degrees Celsius. 21.0 degrees Celsius or 70.0 degrees Fahrenheit. It might have been a shade under 70. I'll write that one too. Okay, so 2014, 70 Fahrenheit, 21 Celsius. Okay. We don't have to repeat this experiment. If we take our measurements today, we can just do the math later. And not make a mess again. So, here's the difficult part, the part that you wouldn't really necessarily have to be expected to do on your own. So number 4 says vinegar is a 5% acetic acid solution in water. So, if we look at that, it's a pretty weak solution. So we can assume that the density of that solution is equal to the density of water. It's actually a tiny bit less dense than water, but it's not particularly significantly less dense than water. So we're going to assume the density of vinegar is 1.00 grams per milliliter, just like water. So we need to find out how many grams of acetic acid are present in our sample. So I'm going to put that on the board for you. And then we're all going to type it into our calculator, because since we're using 40 milliliters instead of 25, I don't have the answer. So we're going to make sure that we don't make a mistake. Also, every lab group is going to need a graduated cylinder with 40.0 milliliters. So you two. Yep. You guys. And I'll run Jolene in there, because we really need 6. And every lab group will get one of these.
In the Chick-fil-A beaker.
Yeah, I know. They're pretty good though.
Kids know the ones, yeah.
Hold on. Did I not have enough rollers? Oh, Jenny, pass yours down. There we go. Okay. So, everybody's going to need their 40 milliliters of vinegar. And so I want you to measure it out carefully, and I want it to be sitting in front of you while we do this math, because I want you to remember every single lab group is going to have the same amount of vinegar. When you
Just as
forget
ours
that,
looks contaminated.
awesome.
I might want to write that down for Eric.
You can just rinse it out. It's always better to, clean your, oh, I know what that is too.
Oh no.
Okay, let's see what happens.
Boom.
What is it?
I'm going to let that soak for a little while, and you guys can just, use mine. So get 40 milliliters, which is 40 grams because, the density is about 1. Everyone can measure out your 40. And I'm going to put the math on the board for how to do that. So because we're using a percent, like the vinegar says on the bottle, it's a 5% solution. So we're going to say right here, that's 2 significant figures. So I'm writing acetic acid, which is this. I'm just going to write the word so you guys can keep it kind of straight. So when you look at that 5% acid solution, what it's saying is there's 50 milliliters of acetic acid in every liter of vinegar. That's what 5% solution means, right? And then we're going to multiply it by the density. And when we multiply by the density, we're using the density of water because it's basically almost all water. Then we're going to multiply by the molar mass of vinegar. All right, so now we're canceling out milliliters of acetic acid with the density, and then we're going to cancel out grams that we got from the density with grams from the molar mass that we found in step 2. So then we're going to multiply by the amount we're going to use to cancel this liter from the 5% vinegar solution. So if we're using 40 milliliters of vinegar, how many liters is that?
0.04.
And we can keep these 2 significant places too. Perfect. So then we multiply here by 0.0400 liters because that's the amount in your graduated cylinder. Okay? In graduated cylinder. That's why I want it in front of you. So you're seeing that 40 milliliters, which is this right here. All right, so now that cancels this liter right here with this. This is definitely not something I would expect you to be able to do on your own. If I just said it's 5%, figure out how much is in there. So step by step again. Let me move the camera because this is kind of the trickiest part. So we've got vinegar, which is a 5% solution. Zooming. So that means that there's 50 milliliters of acetic acid in every liter of vinegar. Then we use the density of water because it's essentially all water. And that can cancel the milliliters of acetic acid with the milliliters in the density. Then we use the molar mass, which we found in step 1, to cancel grams with grams. Then we use the amount that we're going to put in our graduated cylinder and experiment with 40 milliliters or 0.04 liters with 3 significant figures to cancel liters from our percentage amount. That leaves us with what for our unit when we get that answer? This?
Uh-huh.
Well, if I converted that to scientific notation, it would be
never mind, you're right.
4.00.
Yeah.
So it has 3. Because when we measure, it's gonna have 3. So if I type this into my calculator, everyone do it, I don't know the answer either. So I'm gonna type 5 times 10 to the 1, which is 50, times 1, which doesn't do anything, divided by 60, times 0.04, and I get,
What's that thing after the 0.04?
that's a liter that's canceled out with this liter right here.
Okay.
Because this is in the denominator, that's in the numerator. Even though they're far apart, they can still cancel because I'm just multiplying this giant thing through. Now, how many can I keep? Okay, 2 here, so that's my limit. So I can only keep 2. So I get 0.033, and what unit didn't get canceled finally after all of that goes through? Moles. HC2H3O2, and that is acetic acid. So, what does this mean? This 0.033 moles of acetic acid. Why is that number important to us? Why do we care about that?
Because that's, in relation, that's how many, it's the same amount as 40 mils.
Perfect. Now hold up that 40 milliliters. Here's Saul with 0.033 moles of acetic acid in his graduated cylinder. That is the significance of this. Okay? That's how much is in your graduated cylinder right now. 0.033 moles of acetic acid. Okay? So write it down. Hopefully understand it. But if not, just realize that that's how we figure out how many moles of acetic acid are in your graduated cylinder during this experiment.
Will we learn how to do that later in the year, or is it just?
Yes, except we never use percentages like that, because vinegar is about the only thing that you get that just says 5% on it. They'll usually start you out with something a little more convenient than that. Okay, so now we have moles of something, and once you have moles of one thing in a balanced equation, what do you know?
Moles of everything else.
Everything. We know everything now, so we're all set. Right. All right, so what's the question? How much baking soda will it take to exactly react with no leftovers of anything with this much acetic acid? So that's what we have to figure out. How can we figure out how much baking soda we need if we have this much vinegar?
That's over 1 multiplied by 1 mole of the 1 mole of acetic acid goes on the bottom.
Okay.
Yeah, 1 mole of baking soda over 1 mole of acetic acid.
There we go. That's better.
Then the moles of acetic acid cross out. And then the answer would be 0.33 moles of baking soda.
Is it 0.33? Yes. So that's sodium, hydrogen, carbonate. Okay. So, we used a balanced equation. We knew one thing, now we know lots of things. So if we start out with that much vinegar, we cancel out vinegar, we get another reactant. Now we know that to react fully with the vinegar, we need 0.033 moles of sodium hydrogen carbonate, or baking soda. All right, so I'll pass out the scales. You guys just measure me out 0.033 moles of baking soda. Anybody having trouble yet? Have we spotted the problem?
You said we need to measure out moles. The scale measures in grams.
Aha, there's the problem.
Units.
If only it had a mole button, we'd be all set. What are we going to do? We know moles, but we need grams.
We know that
Ah.
84.0 grams are in 1 mole. So
Oh, wait a minute.
divide that by 0.033.
Good. So we know how to convert moles to grams. Oh, I make a mess. So everyone do a conversion to convert moles of baking soda to grams of baking soda, and then we'll be able to measure it out. Also, I think we're pretty well going to have to use coffee filters to do it. So once you know how many grams you'll need, you can use the scale to measure it. Make sure that the coffee filter doesn't touch the sides of the thing, even if you have to rip the coffee filter down to make it fit. Oh wait, don't start measuring yet. We're not all gonna measure the same amount. That would be silly. We could just do it once if we were gonna do it that way, right? So don't literally start measuring yet. Let's think it through a little. And we can only keep 2 significant figures. So it looks like our goal here is going to be somewhere around, did everyone get the same thing I did? About 2 grams. So if we convert moles of baking soda using our molar mass of baking soda that we found in like step 3 to grams, we'll find 2.8 grams of baking soda to be exactly what we need to react with 40 milliliters of vinegar so that nothing is left over. Okay, so do you think that what we found mathematically is going to be what happens in the real world? I really hope it is. Okay, so we're aiming for 2.8 grams. Let us consider how we could do a good experiment to see if 2.8 grams is really what we want. So if we have 6 lab groups and we want to design an experiment to see what's going to happen, what should we do? Should everybody do the same thing?
No, each lab group should do a different amount of baking soda so that it takes less time because we have 6 groups.
Right. So we're going to have one group definitely do 2.8 grams because that's what we think the answer is going to be, where we'll make exactly the right amount. So then maybe a few groups do less, a few groups do more. Yes? All right.
Agree
So
with the 2.8.
how much less, how much more?
10 grams less, 10 grams more.
0.10. 10 grams less would be like negative 8 grams, if that's right. Maybe like if we started with half as much,
Yeah, I think we can do
and then maybe somewhere in between. 2 point what would be right in between?
2.
2.2 grams. So we're adding like 0.6 grams each time. So
No, it'd be 2.1, I think.
2.1.
I think. Yeah. Because then 7, difference of 7
7
and
down. 7 down. Okay, so if we went 7 up from here, 0.7 grams up, we'd get 3.5. And then 0.7 up from that.
4.2.
Okay, so these are our goals for the groups. What would you predict the limiting reactant would be for the group that gets 1.4 grams?
baking soda.
Okay, from now on, when I say LR, that means limiting reactant. So we're predicting the limiting reactant for this group is baking soda. All right, for this group, what will we think the limiting reactant is?
Baking soda.
This is important stuff to write down. Although it may not be the case, we might find the real world answer doesn't agree with our math. How about this group? What's the limiting reactant?
Error.
Not error.
There
No, like
was-
error,
there should be
like there's a
no
problem.
limiting
Oh, what's the
reactant.
problem?
Well, like if there's if someone accidentally puts a little bit too much in, and
Okay, well, we are actually going to write down the real measurements here in a minute, once you guys do the scales. Like if you get 2.2 grams, then we're gonna write that down and use that instead of 2.1 grams. But what would the limiting reactant be if we had 40 mils of vinegar and 2.8 grams of baking soda?
There shouldn't be a limiting reactant.
Perfect. So no limiting reactant mathematically in this one. That's called equivalence point. So they're equivalent moles of vinegar and baking soda in this, if our math is good. How about this? What are the limiting reactant, the one that runs out first, be for 3.5 grams of baking soda?
Vinegar.
Okay, so vinegar is limiting reactant here, and of course here too. All right, so in your lab report, it'll be important to note your prediction, what's going to be the limiting reactant in each run. Now, everyone's going to measure, and we're going to write down the real amount, and then lab partners are going to cooperate. So what you can do is pour now your vinegar into your Erlenmeyer flask, making sure it all